Hello and welcome to Sunday's edition of Cracking a Cryptic, where I am going to start today with a birthday, and that is to say a very happy birthday to Jojo81. I think Jojo81's real name might be Owen, but Jojo81 constructed the puzzle on our screen, which is called Irregular Whirlpool. And this is the puzzle that I'm going to have a go at in this video. Now, the reason for having a go at this is that Jojo81's friend Scott wrote to us, and Scott said that Jojo81 is one of the first people that they met in the Sudoku community when they started getting into variant Sudokus, and Jojo81's become one of their best friends, and this apparently is Jojo81's very best puzzle, and it was described as being criminally undersolved. Yeah, I think it was that was the wording. Anyway, Mark had a go at this puzzle, and he said, this puzzle has been criminally undersolved. So this is going to be absolutely worth our time, and I hope, Jojo81, it'll make for some sort of suitable birthday present from us to you. That, of course, relies on the fact that I will actually be able to solve it. I have no idea how hard this is. Mark didn't tell me, and I looked on Logic Masters Germany to see if I could glean any information from there, and alas, only 11 people have ever solved this since it was released in May 2022, so in a year. That suggests, I suppose, it might be quite difficult, but there's not even a rating, so I literally cannot tell. But anyway, I'll read you the rules in a moment. Actually, no, I won't. I just want to take a moment to express my admiration and slight fear about this puzzle, because it is very beautiful. We've just got 1, 2, 3 and 4 as givens, and weird irregularly shaped regions, and a few cages and a few arrows. I mean, it's basically completely rotationally symmetrical, isn't it? I mean, apart from the arrows. What I mean by that is, if we just twist the grid, if we ignore the givens and ignore the arrows and just twist the grid 90 degrees, we're going to keep getting something that looks very similar to itself. I suppose the cages are all a little bit different as well, but it strikes me as one of those puzzles that is minimalistic, and that's slightly worrying. But anyway, we'll have a go in a moment or two. I have got other things to tell you about first. Not many, though, today. I'm going to wish somebody else a very happy birthday. Over there in Virginia, in the US, Elizabeth, you have turned 32 today. And I know this because your partner of 10 years, Cody, wrote to us and said that you would appreciate a shout out. I think you've been watching for a while. Cody said you both know the secret, but you're very good about it and you never tell anybody else. Well, that is lovely to hear. Well done on protecting the secret. I myself have looser lips on occasion, but Elizabeth, I hope you have an absolutely brilliant birthday with lots of cake, of course. Oh, and just really a reminder, if you are a patron of the channel, or even if you're not, and you have some puzzle time to spend, do spend it in the company of DiMono and the Jewels of Osiris, which is our Patreon reward for May. It's a Sudoku hunt like no other, literally like no other, because it comes in the form of a novella. And in order to read the whole story, which we are being told is very much worth reading, I mean, I've read it, I agree, it's worth reading, but I'm biased. But if you want to read the whole story, you've got to solve the Sudokus that crop up along the way. It's really quite something, and you must check it out. And I think that's all the news. It's weird at the moment because I don't have a great long list of names to read out this month, because we're going to do the shout out slightly differently once the 20th of May arrives, which is the deadline day for the Jewels of Osiris. But anyway, that means we can get on with the puzzle more quickly. And let me read you the rules of Irregular Whirlpool by Jojo81. They are as follows. Place the digits 1 to 9 once each into every row, column, and 9-cell bold outlined region. Now, I haven't checked this, but I'm presuming, yeah, that's got 9 cells, which means all of these sort of rocket-shaped regions are going to have 9 cells in them. And then it looks like we've got, is this 9 cells? Yes, it is. Okay, so the Eiffel Tower shaped region, which also crops up, look, everywhere around the grid. That also has 9 cells. So each one of these regions, and there must be one, there are 8 of these, have the digits 1 to 9 once each in them. So these serve as our 3x3 boxes in terms of normal Sudoku. And that, I suppose, means that these cells, which are not 9-cell regions, but because we've got 8 different regions made up of the Eiffel Towers and the rockets, and there must be 9 of each digit in this puzzle, we now know that this set of digits here is a sort of disjoint set of the digits 1 to 9 in this puzzle, which might be useful. I don't know if that counts as solving to say that. I don't think it really does. Digits along an arrow must sum to the digit in that arrow's circle. So we add up these 2 digits. If we'll be a bit careful. Let's make that 2 and that 3, and then that would be 5, because 2 plus 3 equals 5. Digits in cages sum to the small clue in the top left corner of the cage. So that's normal killer Sudoku rules. So those 3 digits sum to 14. We don't even have the opportunity to put in a repeated digit in any of these cages, because they are all part of their own rockets. So we don't need a rule about no digits repeat in cages. It would simply be impossible in this puzzle. That's all the rules. So do have a go. The way to play is to click the link under the video as usual. But now I get to play. Let's get cracking. Let's get rid of that 2-3 pair there. Now I can see one thing. Let's do my one thing. This cage here is 3 cells and doesn't contain a 1. Well, there's only one way of making 3 different digits add up to 10 if you can't use a 1. It must be 2, 3 and 5. Which means that... what does that mean? Absolutely no idea. No, I was about to say there has to be a 1 in this 10 cage, but that's not true. Although there can't be a 2 in it, if there was no 1 in it, it could be 3, 4, 5, couldn't it? So it doesn't have to have a 1. It nearly does. Okay, so we've got a 3-cell arrow here, so 3 different digits on an arrow. If we made them 1, 2 and 3, which is the minimum we could make them, we'd get it to up to at least 6. So this square must be 6, 7, 8 or 9. Same is true of that one. Wow, okay. What is going on here? I have a feeling this is going to have to be geometric, because there just is nothing. Or in irregular Sudoku you can sometimes find the law of leftovers being helpful, but that doesn't seem to be. Okay, here's a thought. This digit is interesting. Because this cell, whatever digit is in this cell, has to appear somewhere in its Eiffel Tower. Where does it appear in its Eiffel Tower? Well, it can't appear in the same column and it can't appear in the same row. So that digit is on the arrow in this box, and this arrow can't have a digit on it that's higher than 6, because if we try and put 7 onto this arrow, it'll be a minimum of 1, 2, 7, which add up to 10, which is too high. So this digit can't be 1 or 3 by Sudoku. So this digit is 2, 4, 5 or 6. This is, I know, a very loose restriction. And whatever this was, so if this was 6, this arrow would have to be 6, 1, 2, adding up to 9. But that logic, although it doesn't quite work, it works the same way in terms of the Eiffel Tower shapes, doesn't it? So these digits, so what about this one? This digit can't be 2 or 4, but again, we can't have it being higher than 6 because it must appear in one of those 2 cells on the arrow. So that digit is 1, 3, 5 or 6. These two are totally different, because it's still true to say that that digit has to be in one of those two positions and this digit has to be in one of those two positions. But you can see that, well, we know absolutely nothing about, well, I suppose we know that digit's not a 1 or a 4, but I'm not pencil marking 7 cells into this cell here. And the same is true of this one. These two can't be 2 or 3, but they could be anything else. No. No, I suddenly thought, is it Fistemfell? But that's not in the right position to be a Fistemfell ring. It's too exploded, isn't it? The Fistemfell ring is a theorem that says, well, in a normal Sudoku, which is not going to be this one, these in a normal Sudoku, those cells are the same digits as the 2x2s in the corners. But that's not the case here. And goodness only knows what the proof of that would look like in this puzzle, because it normally relies on being able to use 3x3 boxes. I mean, I suspect it's going to be some sort of geometric trick, though, this, because there's just nothing, is there? It looks like... It does look like it's. I don't think it's the Fistemfell ring, but it's something to do with this interior section of cells. Where this is where all the action in the puzzle is. Look, you get cages, which we would know the sum of. Actually, maybe I don't want these cells in, because we don't seem to know a great deal about those cells. Although those 3 cells are on this one's arrow. So often when you get these geometric tricks in puzzles, what you're trying to do is to build patterns. And I will explain this if I can find whatever's going on here. But we want to put this digit and this digit in different sets to their arrows, because then we can just cancel them out of each set. So let's try... Well, let's try the rockets in the first instance, because that way I capture all of the cages and all of the circles in these sort of 2x2 boxes. It's almost like we need to invert the Fistemfell ring somehow. Yeah, I mean, I'm not. My first thought might not be that stupid here. My first thought was to look at this ring of digits, because I could see that I was picking up all of the arrow cells. So I'm not sure about this, but I'm just going to look at it. So I'm just going to highlight all of these cells in orange and just do some cancelling. If this looks like it's going anywhere, I will of course explain what I'm doing, but there's really no point in explaining the whole of set theory if this is just a total and utter nonsense. So let me just do a bit of cancelling down. I've broken this. I've totally broken it. That cannot be true. How much do these cages add up to? A lot. 40, no, you can't make those. What have I done wrong there? Those 2 cells definitely can't add up to 48. Ah! What did I do wrong there? Oh, I know what I did. Look at that. Okay. Okay, let's come back here. If I add on 4 oranges in the corners there. Ah! I've got you. I've got you. Right. Okay. Now we have to unwind all this, because this is magical. This is pure and utter magic. Right. We'll start from here with this rather pretty pattern of green and blue. Now, we look at those blue squares and we might say we know nothing about them, but that's not true. We know basically one thing about the total quantum of digits in these blue highlighted cells, And that's that these blue highlighted cells are 4 sets of the digits 1 to 9. And we know that because obviously this region, that's 9 cells, all of which have to be different. So this is one set of the digits 1 to 9. This is a second set, this is a third set, and this is a fourth set. Now, if you bear with me, have I got my Scrabble tiles? They're on a load of paper. Hang on a moment. Let's grab some Scrabble tiles. Now, here is my blue bag of Scrabble tiles. Now, if I go in here, you can see that written on that Scrabble tile is a 2. Written on this one is a 9 or a 6, depending on whether we turn it, which way up we turn it. Let's find another one. This is a 1. So, what I am proposing that we do is for each one of these blue cells, we write the digit in that cell and we plonk all of those Scrabble tiles that we are left or that we generate as a result of that exercise into my blue bag. Now if we do that, we know exactly what my blue bag contains, because there's going to be 4 Scrabble tiles with a digit 1 on them, because there's going to be 1 1 in this region, 1 1 in this region, 1 1 in this one, and 1 1 in this one. There's going to be 4 tiles with a digit 2, 4 tiles with a digit 3, all the way through to 4 tiles with a digit 9, making up the 36 tiles in my blue bag. Now, I'm now going to highlight some different, or I'm going to highlight a different set, or I'm going to highlight in a different colour another set of, well, another collection of 4 sets of the digits 1 to 9. So let's look at column 2, and I'm going to highlight that in orange. Now, obviously this entire column is one set of the digits 1 to 9. I'm going to highlight the whole of this column. That's another set of the digits 1 to 9. So far we're up to 2 sets of the digits 1 to 9. If I highlight the whole of row 2 as well, that would be another set of the digits 1 to 9. But note, this cell is it's both in this column and in this row. So I need to put that whatever that digit is on 2 Scrabble tiles, because it appeared in this column and this row. This has to appear on 2 Scrabble tiles. Now if I do this row as well, this cell and this cell would each have to appear on 2 Scrabble tiles. So we'll just make those purple for a moment. Now, I'm proposing that I write those Scrabble tiles, the orange Scrabble tiles, with numbers on, and I'm going to put them in this bag. And the thing that you have to get your head around is that obviously if we do that properly, this orange bag is going to have 36 tiles in it as well, and there's going to be 4 tiles in this bag with a digit 1, 4 tiles with a digit 2, etc. In other words, the tiles in these 2 bags at this point are identical. There are 36 tiles and the contents of those tiles is identical. Now imagine that, well, let's take this 1, this given 1. I go into the bags and I find a tile with a 1 on it in this bag and this bag, and I take those tiles out and I throw them away. What then can we say about the contents of both bags? Well, hopefully you would agree that there's now 35 tiles in each bag, but there's only 3 tiles with a digit 1 on now. There used to be 4, but there's now only 3. But the contents of the bags are still the same, because we've got rid of the same digit from both bags. Well, let's say I knew the complete solution to this puzzle, and I did that for all of the cells that appear in both bags. Clearly, I could get rid of an awful lot of awful lot of tiles that way. So let's say I got rid of all of those tiles. And let's deal with these corner ones as well. Now these tiles were twice in the orange bag, but only once in the blue bag. So I could remove 1 from the blue bag and 1 from the orange bag, and I'd be left with 1 of this tile in the orange bag. So these can be cancelled down to just 1 orange tile. And we arrive at this situation. Now at this point, hopefully you would agree, because we've been removing the same tiles from each bag. Whenever we took a tile out of one bag, we took whatever was that digit, we took it out of the other as well. Whatever's left, these Scrabble tiles, the orange Scrabble tiles and the blue Scrabble tiles, are the same. They have the same digits on them. So there are 16 blue tiles, there'll be 16 orange tiles, and they have the same digits on them. And this, I think, is absolutely wonderful in this puzzle, because now we can go a stage further. If the Scrabble tiles are the same, and they are in the blue and the orange bag, what's the sum of those tiles? And the answer is, we haven't got a Scooby-Doo. We do not know. But we know whatever that number is, x, the sum of all the Scrabble tiles in orange, it's the same number x that's the sum of all the Scrabble tiles in blue. Now, we can use the property of arrows then, because we know that this arrow here, these two cells, add up to that one. So if I took these two tiles out of the orange bag, and I took that tile out of the blue bag, I've now got a different number of tiles in each of the bags. But the sum of all the tiles, sum of all the digits on the tiles, is still identical. I can do that for this arrow as well. I'm going to go and hunt for those three cells in the orange bag, and I'm going to remove that one as compensation from the blue bag, and I'm still in a situation where the sum of the tiles is the same. Even though the number of tiles is different in the bags now, the sum of the tiles that remain in the bags is still the same. I can keep doing this. Oh no, let's do it with the right arrow. That one. And I arrive in this situation, where I've got 12 digits now, or 12 tiles left in my blue bag. But the absolutely wonderful thing about these 12 tiles is I know what they add up to. They add up to 48. And and we know that the orange tiles here must therefore add up to 48. How on earth do we make these 6 cells add up to 48? Well, there's only one way. If we put 7, 8, 9 in this row, they add up to 24. And if we put 7, 8, 9 in that row, that gives me another 24. There is simply no other way we can make the oranges add up to enough. So that is absolutely gorgeous use of sort of set theory. I'm sorry to labour the point. I know many of you, well, you could see I could do that very quickly because I'm used to set theory. So if I wasn't explaining it, it's a 20-second mental exercise. But if you've never seen it before, it's definitely not. It's like magic. It's completely like magic. But hopefully the Scrabble tile analogy, at least it helped me to crystallise in my mind what was going on. Now what do we do with this newfangled or newfound information? Well, oh, please don't tell me this does. I mean, it must do something. This is quite clearly deliberate. Probably. Oh, okay. Okay. All right. That digit I can now write into the puzzle. This is just sensational. I mean, we had an absolutely amazing naked single the other day. Can't remember what the puzzle was now, but this is up there, isn't it? So look at this row of the Sudoku. We need to place 2, 3, 5 and 6. Well, that square can't be a 2, 3 or a 5 because 2, 3 and 5 are in the same region as it. So that square is a 6, which means these squares are 2, 3 and 5. Okay, and now look at this arrow. Because this arrow can't add up to 5 because there's already a 5 in this rocket region. So there must be a 5 now on this arrow. This can't be a 5. So this arrow either adds up to 7 or 8, depending on whether we accompany the 5 with a 2 or a 3. Okay. Now what do we do? Probably the same thing on this row. We need 1, 4, 5 and 6 this time. 1, 4, 5, 6. So we're nearly at the point where this needs a 1 on it. It doesn't quite need a 1. If it didn't have a 1, this would be a 9 because it would have to be a 4, 5 pair. This cell's not a 6 by our old friend Sudoku. A fair weather friend. Oh, bobbins, come on, Simon. What is it? Oh no! I must be able to say something about this now. we can... I see. Alright, I can say one thing about column 2 now, I think. Actually, has this been available for a while? I think it has. I didn't appreciate this. 3 in column 2. Where does it go? Well, it's not here. And it's not there because of this 2, 3, 5 triple. So there's a 3 on this arrow. And that means this square can't be a 7. Because we can't make this arrow a 1, 2, 4 triple. Two, 5. 1, 2, 5. I'm sorry, I'm not spotting what I meant to do here. This is confusing now. What on earth am I meant to do with this new information? I'm sure it's really interesting as a pattern, this, because I thought what would happen is once we got this sort of lovely 7, 8, 9 triples, or once we got these 1, 2, 7, 8, 9 triples, we would just finish the puzzle. But that's most certainly not what's going on. Okay, where does that digit go in this region? And I think, because it's not 2, 3, 5 or 6, whatever this is, it goes there. And that means this square is not a 9, that is a 7 or an 8. And those two cells are the same, so I'm just going to label those with an A to keep track of them. Those two digits must be the same. It doesn't look like they should be the same by Sudoku, but I think that they do need to be the same. 2. I'm wondering about... Okay, 4 in this region, look. Where's 4 in this region? It's in one of those two cells. So now, I feel like this 12 cage is under pressure, but I'm not sure I can prove it to you. What I'm thinking is, if we look at... Hang on, let me think about this. I've got 2, 3. Well, no, 3 is dealt with. I've got 1, 2, 4, and 5 to place somewhere in this column. Now, if 4 could be here in box, whatever box this is this box 7? If 4 is there, what does that mean? Oh, I still can't see it, you know. This is not 3, 4, 5. It's definitely got to have a 1 or a 2 or both in it. This digit could be the same as this one, I think. Oh, 6 is seeing this one. I didn't spot that, look. So this is 8 or 9. Ah. No. Oh, yes. Yes. Okay. Goodness, this is quite complicated. Right. Let's have a look at this circle. We can see that this circle, if this is 8, well, it can't be 8 now because there's a 3 on its arrow, and it would have to be 1, 3, 4, and the 4 is not available. So this is 9. That's huge. So this is 9, although somehow that 9 doesn't see anything. I thought we would get something in orange as a result of that. Right, oh, okay, but now we know what this arrow is, I suppose, because if it's 3 cells that add to 9, that don't include, well, that include 3 and don't include 4, it must be 1, 3, 5. Okay. And is that helpful? 1, 3, 5. So now in this column, we've got 1, 3, 4 and 5, which can't appear here. One of them, so 1, 4 and 5, 2 of 1, 4 and 5 have to be in this 12 cage. And one of them is there. So if this is a 1, no, this can't be a 1. Because that would put 4 and 5 in this 12 cage where they'd need to be accompanied by a 3. So this is not 1, this is 4 or 5. If it's 4 in here, then I have to put 1 and 5 and 6 in there. Is that a problem? That might be a problem, I'm not sure, but that's one option, 1, 5, 6. If this is 5, on the other hand, I then have to put 1 and 4 in here along with 7. Okay. Okay, well what that means is that now we can ask where 8 goes in this region. And 8's got to be vertical, look, which means this square is no longer 8. Oh, but this is the one that could be the 9, or it could be a 7 in there. Right, so what does all that mean? Well, 2. Where does 2 go in this column? It doesn't seem to be able to go in the 12 cage, so it's got to go in one of those squares, and it's not in that one because of this 2. So sorry, what we need to do is to corner pencil mark the 2's. It's still not quite done, this, is it? When I say not quite done, that is a euphemism for not done at all. Okay. Oh. Hang on. If there's an 8... No, a better... Yeah, okay. So what I did was I got rid of the 8 from here, but a better question is where does 8 go at all in this top cage? It's got to go there. And that's the A. That's the same digit as this, by the logic that we did earlier. So now these are not 8s. This is not 8. And now where does 8 go in the top orange set? It goes here, which means this isn't 8. Good grief. Right, these two squares add up to 8, so they've got to be 3 and 5, which means this square here is a 2. Now I must know what they... Well, I know that this is a triple from 4, 7 and 9, which means this triple at the bottom here is from 2, 6 and 8. So I've got a 2, 6... if I've got a 2, 6 pair here, I'm not allowed to put 6 in the 12 cage, which means that the 12 cage is not 1, 5, 6, it's 1, 4, 7, and this square becomes a 5. These squares are all now not 5. And now there must be a 1 on this arrow, because otherwise it would be a 4, 6 pair adding to 10, which means this isn't a 1. There's definitely a 1 in one of those two squares. 5 is placed in the 2, 3, 5 triple. Good grief, this is just... I mean, it's weird. I'm sure I'm missing things here, but it feels like the way the geometry works is just strange. Right, remember the Eiffel Tower trick? That digit has got to be the same as one of those, so that is a 3, 5, 7 or 9 now. Well, this that one's a lot. 1, 4, 6, 7 and 9. That one is 5 only. Oh, this is lovely. This one. This is where we look. This Eiffel Tower. Where does that digit appear in that Eiffel Tower? Well, it has to be in one of those two squares. That's a 5. That's probably been available for ages. 5 goes here in this sequence. 5 doesn't repeat, remember, in green, because remember what we worked out at the start? We worked out that this was a disjoint set. So it's the last of each digit in the puzzle. So that can't be 5, that can't be 5. Oh, no, I was about to say this can't be 3 because I was looking at this 3-5 pair thinking it was in its region. But actually, well, if that is 3, that's 3. Oh, blimey, 5. Oh no, it's fine, it's fine. Okay, here is quite an interesting question. Where does 5 go in row 1? I was looking at this 3-5 pair. Now, we know 5 doesn't repeat in green, and if 5 can't go in those squares, so actually it's got to be there. I was looking at this square thinking it could be here, but that's not true. So how many 5s have we got? We have got 5 5s and a 6th 5 in one of those 2 squares. Is that helpful? I'm sure it is in some way or other, but I don't know what that way is. 5 in... Okay, 5 in the bottom row. Let's ask that question. Now I think, because it can't go in green, it's in one of those 2 cells only. Which is not amazing, but perhaps worth noting. 5. Oh, in fact that's lovely, I think. Where does 5 go in the central column of the grid now? If 5 is here in the bottom row, it can't go in those squares, it can't be in green at all. So it is in the top Eiffel Tower, but we know that the 5 in the top Eiffel Tower is in one of those squares as well. So the only square that overlaps with those criteria is this one. So that's 5, that's 3. We can't use that to prove. Oh no, it doesn't stop that being a 3. Oh, and I've not been looking for 3s in corners. Look, that one is a very naughty digit, because that removes 2 possibilities for 3 in corners. So we need a 3 in one of these 2 cells. Somebody wrote to Sven actually yesterday to say, why when I put 3 into the corner of the software, is there this animation of a party popper? And they sent him a video of the animation. And Sven asked me if I would go over again why sometimes if we put 3s in the corner. Let me just show you. I'll put a 3 there because it will do it, I think. Yeah. It doesn't really deserve a song, but the reason we do it is that about a year ago or so, I think I've been listening to too much REM and losing my religion. And there's the line, "That's me in the corner." And somehow my brain said, "That's 3 in the corner." So whenever there's a 3 in the corner, we sing. And that's why the party balloons go off. Oh, I know what I can do here. I can use the secret. So Elizabeth and Cody, I'm very pleased that you haven't let anyone know the secret. As you know, I'm slightly more inclined to let the secret out when necessary. And if you're still watching the video now, you definitely deserve to know the secret. The secret is that any complete column, row, or 9-cell region of a Sudoku contains the digits 1 to 9 once each, and therefore sums to 45. Now, can't we use that to get the value of these 2 squares in this box? We've got 14 here. That's 20, so 33. So these 2 squares have to add up to 12, and that is absolutely brilliant. Because how are we going to make these 2 squares add up to 12? We can't do double 6, we can't do 7 5. There's a 5 in the region already. So we've got to do a 9 and a 3. Okay, that still does some things. 3 and 2 going over here. This 14 cage is now filled with 617, I want to say, which somehow doesn't do anything. Oh, okay, yeah, lovely though. This arrow adding up to 9 without using a 3 or a 5, well, it's got to be 1 2 6. That's the only thing it could be. 2 3 4 and 1 3 5 are ruled out. Now this square can't be a 3 now, because remember, for this Eiffel Tower, this digit goes in one of those two squares, so 3 is out of the question. So this is 1 or 6. This looks like I've broken this, doesn't it? Looking at this quadruple, it looks like there's not enough different digits there. Okay, but if this is a 1, 2, 6 triple, what do we need at the bottom? We need 4, 7 and 9, which is the same as that. 4, 7 and 9. Oh, look, if that's 4, 7 and 9, that square is a 6, which means our arrow here adds up to 5. Okay, that's useful. This square now is not a 6, because it must be the same as one of those squares on the bottom Eiffel Tower. And using this knowledge, well, we now know this cage, I suppose. This cage has got to have an 8 in it, so this is 1, 3, 8. So I can see that means this square isn't a 1. And the way to get that deduction is to look at these two rows together and ask how many 1s we think there are going to be in those two rows. And hopefully your answer is there will be exactly 2 1s in these 2 rows of the grid, because if there were 3 1s, you would necessarily repeat a 1, and that's a bad thing to do in Sudoku. So we know there's a 1 there, we know there's a 1 there, so if this was a 1 as well, that would be 3 1s, and that would be jolly naughty. The same sort of trick, look, could be done in these 2 columns. Oh, in fact, look, we've got a 3 here. 6 here. We've nearly... no, we haven't. I was about to say we've nearly used all the arrows, but this cell looks like it might be worth investigating. We don't know what we're heading up towards. If this is 7, this couldn't be a 7. This would be a 6 or a 3. That's quite unbelievable, because both of those options seem to be available. If this is 9, this could then also be 2 or 5. No, it couldn't be 5 or 8. Oh, goodness. Okay, well, that's infuriating. This square doesn't seem to be restricted at all. That 3 is giving me a 3 and a 1 over there, though. So 3 and 1. That's lovely. That 4... Oh, this is lovely. This is lovely. This one, combined with what we did with the 1s down there, plonks a 1 there, which makes this a 6. It makes me think I've broken the puzzle again. I think I've got 2 6s in this region, but it's hard to realise that the bottom of the Eiffel Tower isn't part of the Eiffel Tower at all. Okay, this 1 is placing a 1 here. That gives me a 7 and a 6 and a 2 and a 6, which surely does some things. Well, this arrow total now we can narrow down. That's 4, 8 or 9, I think. Can we do anything with that? Surely it can't be 4, can it? No, it can't be 4. Because the minimum value of this, in fact the minimum value of this square is not even 3, it's at least 4. This is at least a 4 because it sees a 1, 2 pair in its Eiffel Tower and 3 in its column. That square is at least 2, it sees a 1 already. And that square is either 2 or possibly 4. So but it can't be 4 because that would make this arrow add up to 10 already. So this square is definitely 2, whatever goes on. But I think these two could... We still don't know whether this is 8 or 9. Which is infuriating. Well, this square's either... Whoopsie. This square's either 2 or 3. This square's either 4 or 5. Oh, sorry, no, hang on, there's a 5 here. This is not... This is definitely 4 then. So this is 2 or 3. Come on. I can't see how to do it. But this square's become a naked single 8 because it sees 1, 2, 3, 4, 5, 6 in its column and 7, 9, sorry, in its row and 7, 9 in its column. So that's 8, that's 8. This is a 1, 3 pair. We still need 7 and 9 into these two squares, which include the middle cell. that one, that's going to do that. So that's 7. That's 9 in the centre. So 9 comes out of the green cells. And that's going to be important for the following reason. Come on, brain, think of a reason. Here's a different question. Where's 3 in the top row? 3 is not allowed to be here by Sudoku. And in this Eiffel Tower, 3 is vertical. And 3 is there. So that's a 3. And that is going... Oh no, that's a disaster, I've just realised. Well, really it was the fact there's 3s here. We can't put a 3 in this corner. So we're not actually going to get to sing the song, I'm afraid. Bobbins. Right, okay. I've got something. Right, this 7 means there's a 7 in this domino. And that means that square's a 9. And this square's a 7. And this square's a 4 now. It sees 9 in its row. Right, that's all good stuff, isn't it? So can we now... This is 8. Oh, this is 8. It sees 9 in the column. And that means this is 2 to make the maths work. So that's not 2. How do we finish this off? Well, let's have a look at this column. 4 and 5 to place. So that we can do the 4 at the top because it sees 5. That must be 5. Let's look at this column. Can we get this digit? Oh, we still got to do this arrow. That's probably why we're being held up. Let's try... I don't know. Let's try this Eiffel Tower, shall we? 1, 2, and I want to say... Oh, this is horrible actually. No, it's 1, 2, 6 and 7, isn't it? I didn't realise that. No, that's a naked single 1. It sees 2, 6 and 7 in the column. Right, let's just label all of these up and try and investigate them individually. That's not 2. That's not 6. That's not 2. So this is the 2. In this column, is this... This is not 8 anymore. Ah, not 8. It sees 8 here. The 3 gives me a 6 here. Okay, so that's going to do some work, I think. That means this is 7. I get a 1, 4 pair at the bottom, but this 6 is presumably going to help with this. This can't be 9 now because this can't be 3. So that's 7. This is 9. This square here is a 1. So that's 1, 4, 7 to go in. 6 goes in up here. 1, 4, 4 go there. 4, 7, 1, 3. Okay, that feels a little bit better. 2, 6. Well, let's try and do this by disjoint set, shall we? 1, 2, 7 and 8. Okay, let's put 1, 2, 7 and 8 into the corners and try and make sure these are all different. So you can see we've got a 7, 8 pair at the top, so we can knock 7 and 8 out of the bottom. And the 1 here is very nice. So 2 and 1 go in. Let's have a look at this row. 5 and 6 to place. Yes, we can do that. This row. 4 and 9 to place. Yes, we can do that. This row. 9 and 3. Well, we can do the 9 now. This row. 7 and... Oh, 7 and 8, but this time it's resolved because that 7 pokes in and sees that digit. So that's 8, that's 7, that's 8, that's 7. And we've just got the bottom row to do where we need 3, 8 and 9. So that's 8, that's 3, and then if I haven't made a mistake, that's 9. And that is one of the best puzzles you will ever see anywhere in your life. Yeah, I did it in no time at all. It was so straightforward, I cannot tell you. No, that was not straightforward, and it was absolutely lovely. I don't do nearly as many set puzzles as I used to on the channel. But that's probably because there are so few examples that are as simply beautiful as this one, and it was quite well signaled, to be honest, because there's just nothing you can do at the start. I mean, there's just not enough to get your teeth into. Maybe I could have got a 3 on this arrow, but what would that have told me? Nothing. very little. It would have ruled out 7 from here. But that's about the limit. You've got to really work to use all of the, the combination of the arrows, the cages, and the geometry to give you this weird 7, 8, 9 arrangement. And even then, was it that digit that was a 6? That was just gorgeous. But after that, it wasn't easy, at least not for me to solve it. You still had to use the Eiffel Towers a bit. I mean, it's just exceptional. It's such an exceptional puzzle. The choices of the circles, so that that they revealed things at appropriate moments rather than disturbing any of the earlier logic. I loved that. Jojo81, happy birthday, and I hope you enjoyed me wrestling with your puzzle. I certainly enjoyed wrestling with it, and I thought it was marvellous. Let me know in the comments how you got on. I enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.